we saw that because we have excess spin up protons in a strong magnetic field, that we end up with a magnetization vector pointing in the same direction as that magnetic field. Now, because we have the magnetization vector, we can probe it to figure out information about the molecules in question. So if I apply a magnetic pulse, like bringing a nearby magnet, I'm going to nudge this magnetization vector just a little bit. So once I nudge that magnetization vector, it'll no longer point in the same direction as the overall magnetic field. Anytime we have a magnetization vector out of line with a magnetic field, we see that we get a torque. And because this torque does not coincide with the spin of the molecule, which is described by m, it'll begin to rotate or precess around our external magnetic field. Now in MRI, one pulse isn't going to cut it. So instead, we keep pulsing the object until we can get it to precess all the way down to the plane we want. How fast do we pulse these objects? Well, we have the Larmor frequency. So the Larmor frequency depends on how strong the magnetic field is around your magnetization vector, or the slice you're looking at in the head. So if I have a really strong BZ, I will have to apply a frequency a lot faster to get it to pulse down so that we spin in the XY plane. Now, once we stop pulsing it, what's going to happen is that the magnetization vector is going to spin back up to point in the positive Z direction. So we can actually quantify how quickly it comes back to rest at the stable equilibrium and figure out what different parts of our body actually look like. So the first thing we want to look at is the MZ part, so the amount of magnetization vector in the Z direction. Well, when we're fully flat in the XY plane, on this piece of paper, we have no component in the Z direction. So we know that's going to have to restore back to the Z value we originally had. So this equation will describe it, where m0 is just however much we had initially, and then t1 represents the time constant of relaxation to restore mz. Now, when we had this precession that went all the way down to the plane, we created an mxy component of our magnetization vector because it was now rotating in this perpendicular plane. As it comes back up, it's going to lose that value because it's only in the z direction, so we will have exponential decay described by T2 star, which represents the decay of the mxy component. Now, these two pieces, T2 star and T1, are how we actually image in MRI. We can take images that differ on T2 star and T1 star, just T1, and give different pictures of what our head or our foot or our hand looks like.